used to teach, to my students, rather than a conference presentation or something like that. Okay, so in the conference presentation, we are actually very formal and then I present, although then audience needs to wait and then they can ask questions. But if we, follow the class, so that means you can stop me at any time and you can ask me questions. Okay, and I'll be more than happy to answer your questions and then move on. Okay, and also I don't think I'm going to be in a hurry. Whether I will, try to go with the pace of the class. Okay, if you want me to, explain more in any of the slide, I will be happy to explain more and then move forward from there. Okay. Okay, so let me introduce myself briefly. So my name is GIAN. Mostly I am actually more familiar with my academic name, MP GIAN. So if you are following me or maybe my microarray research, you may see MP GIAN. Some of our papers are actually one of the top cited papers in microarray research. So, but it happened, several cases. Once I went to a conference at IMACI, and then there is one faculty, he's probably with us from one of the IIT. So he doesn't know my face, but he knows MP GIAN. So he was talking to me about MP GIAN. Then I said, I'm MP GIAN actually. So sometimes my name, MP GIAN is actually, I use that name for most of my publications. So. Okay, so currently I am an assistant professor at the Mechanical and Manufacturing Engineering Department at Miami University. I am also the graduate program director in the department, so that means I am responsible for our graduate programs. And I am also actively involved in American Society of Mechanical Engineers and Society of Manufacturing Engineers. I just finished serving as track chair for Advanced Manufacturing Track at the IMAC, which is ASME's the largest conference, and manufacturing was the largest track. So I just finished serving as the track chair for that, and I'm also serving as track co-chair for Material Renewable Tech, the Society of Manufacturing Engineers NAMREC conference. Okay, so yeah, so I think that's enough for my introduction. So this is the 5-day course. So those are some of the topics that I'll be covering. So first, so I think we need to frame that. Oh, this is here. Okay. So first, today we are going to cover introduction to compound and hybrid machining processes. So hybrid machining processes, it's not a new term now. Okay, it has been a new term when we started working on that, but now I think. Hybrid machine. Now, hybrid process, that term people liked and they started using that term for hybrid additive subtracting. So you nowadays if you see hybrid manufacturing, this is kind of conflict. It can be either of two. It can be either additive subtracting hybrid manufacturing, or if someone is specifically a hybrid machining processes, then it's the machining process. But previously it started with hybrid machining processes, but now when someone says hybrid manufacturing, then it may not indicate machining only. It can indicate hybrid subtracting and additive and subtracting. So I will actually cover some of the basics, and I would like to bring all of you, into the speed, and then we're going to go more in detail about the compound micromachining processes. So hybrid and compound micromachining processes. So there are some differences, okay? But mostly, people use the same term. They just say hybrid machining processes, but it can be, compound, or sequential machining processes, or it can be concurrent or mixed or hybrid machining processes. So there are several classifications. We will cover those, and I think in the next lecture I would like to cover the compound micromachining processes so far, whatever reported in literature. But after today's class, maybe you will be able to think about developing a new hybrid or compound machining processes just by UTSA. For you, like for example, for your PhD topic or your new research area, there are some guidelines you can follow and think, how to solve a problem if you are facing in one of the, conventional or non-conventional machining process, just a single process. And then there are some several guidelines how you can come up with a solution of it, hybrid machining processes. So we'll learn that today. Then we will go more in detail. My plan is for one for each lecture, and some these two may be a little bit, time consuming or a little bit. I'll go more in depth. So after compound micromachining processes, where we cover the process mechanism, process capabilities, applications, and challenges, and then we'll cover concurrent or real hybrid machining processes, where we will cover adhesive-based hybrid machining processes, electro-based, thermal-based, machining processes. Then there are assisted processes that will again go in detail. Then micro and nano EDM has been my research area for last, since 2005, and I will still continue that research area. So in that, I'm going to cover some of the, research that I have done, and also probably share some of the ideas that future research, can be done. And then we're going to, go over hybrid micro and nano machining, current research and future trends. This is the last lecture, but mostly we'll be kind of discussing, okay, like what would be some of the future research areas. So I think I forgot to do one thing that I usually do in my classroom. So after my introduction, I would like to go over the class and kind of at least know each person, so we can probably quickly go over the class, and if you can just share your name and from which institute you came from, and whether you are a student, undergraduate, graduate, or student or faculty. Yeah. Please.
So sir, myself Ivan. So I am coming from PhD College of Technology, south of Tamil Nadu, Bangalore. So I am a research scholar.
That is faculty from your PhD.
That's me. I'm in I did PhD in English process.
What did you?
Thank you. My name is Ricardo. I am from PhD here.
My name is Sudhuleka. I am performing a PhD from University and I'm working with mathematics composed experimental level as some modeling.
My name is Sumit. I'm from Associate Engineering College, West and I'm pursuing BTech in Mechanical Engineering. Again.
Myself, and I'm from Engineering College, from Mechanical Engineering.
Myself, I'm from Department from
My name is Jason and I am doing PhD on mathematics composition and the division of prediction.
My name is Santosh Kumar. I did my BTech at Nano University and I pursued master degree from here and continue PhD solar on the trigonometrical property of the FRP composite.
Trigonometrical properties of that?
Tribomechanical property of the FRP composite.
Nano.
Myself, Mahesh. I am a PhD scholar in the Department of Mechanical Engineering, IIT Kannada. I am a PhD student. Currently, I am pursuing research under Professor K.K. Singh sir. My research area is impact damage analysis of plastic composite. And thank you for your lecture.
Thank you.
My name is Saurabh Kumar Mandal. I am from NIT Jamshedpur. My area of research is flexible supercapacitor.
My name is Saurabh Kumar. I am second year MTech student. Mechanical engineering. I work in the assessment research. My research topic is GIAN.
My name is Ashutosh Kumar. I am doing from PhD under assistant research, Nano composite metallurgical and machining process.
I am currently PhD in ITI Hyderabad, and my research area is biochemistry.
My name is Nitish Kumar. I am research scholar here only, and my topic is hybrid micro manufacturing. I am doing electrochemical desalination process.
Okay, thank you very much for taking time to introduce yourself. I think it will be really helpful to be more comfortable in asking questions. Okay, so as I mentioned, the first lecture will be introduction to compound and hybrid micromachining. We have a few research scholars who are working on those areas, and some of you who are doing maybe you can think of some new area. So first we're going to talk about need for hybrid micromachining. Then we'll talk about the different terminologies that we use, compound and hybrid micromachining processes. Then what are the characteristics and requirements for hybrid machining, the technologies requirement for hybrid machining. Then we'll talk about different classifications based on energy sources. So that's the main thing, or guidelines, if you want to think about hybrid micromachining processes and how you can come up with some new, hybrid machining processes. So that's what I say, how to invest in a new hybrid process. We'll talk about that. Okay. So let's start. Okay, so I know, like, as a engineer, we would like to see lots of pictures, right? So in my other presentations or other lectures, I have lots of pictures, but this one is the introduction. So I mostly try to give a lot of information, and definitely I'll be sharing those materials. So if you read those, I think you'll have some good understanding of some of the concepts. Okay, so I used these three starting materials. So I'm going to cover also some of the course materials. I'll share my PowerPoint presentations, and I will also share some of the published materials that I used. Me and my colleagues, were working in this area for a long time. So I'm sure if you are following media, you also know Dr. Sundaram, right? And also Dr. Ravikar. We're kind of, on the same group, work with the same professors, but now we are, individual, or I would say independent researchers. So this is my book chapter that I have collected information from. This is Dr. Sundaram book chapter that I collected information, and this is Dr. Kapil Gupta. I think his book chapter covered information from. Okay, so these three are the material that I collected information, and then there are some references that I have also cited later on. Okay, so first, why do we need hybrid micromachining processes? So now I will point out to the other, like Dr. Ashwin, because he's trying to create some new mathematics components, right? So what he wants to do is he wants to make our task difficult, right? So he wants to make some materials that are difficult to machine, right? He wants to definitely make things lighter, but at the same time he wants to make like the composites higher strength than higher properties. It can be like higher fighting strength if it is for aerospace applications. It can have higher wire resistance. If you are using for some harsh conditions. So all those properties, higher strength, higher fighting properties, higher wire resistance, definitely making the materials difficult to cut, right? So that means whatever are the current existing technologies will be very difficult to apply to those materials. So you need to come up with some new machining techniques, right? So definitely that is one of the main, reason the hybrid machining process. Then there are some other things like miniaturizations of components. Like I think there have been actually lots of trend in that area recently because of additive manufacturing. It slowed down a little bit, but when we were kind of going through our PhD, that time micro and nano machining was a very hot topic. So the trends were how small you can make. Okay, so my PhD student also kind of always asked, okay, have you machined that how small? So he always wants to know, okay, how small you can go. Okay, so I remember, so our human here is about 80 micron, and I think we were able to machine 5 micron, holes. So he was always pushing the boundary, okay, how small you can go, because there are some limitations about how small you can go based on like the nano power that you are using, or the particle size that you are using to make the random composites also, right? So you cannot, like for example, if you're reading the size to the particle size, that is kind of trying to break down. Then maybe you need to machine individual particle size if you have to go further, right? So then complex shapes, machining of inaccessible areas. So necessity is the invention, right? Like mother of invention, right? So definitely where there is necessity, then you need to come up with new processes like non-circular holes, deeper holes, the machining of low rigidity structures. Sometimes some structures are difficult to machine by conventional machine processes because of cutting forcing to break down, right? So you need to come up with. So those are some of the challenges that actually necessitate the need for thinking out of the box. Okay, there are some processes, conventional processes, non-conventional processes, but probably there is a limitation. So how you can combine different energy sources, okay, to come up with a new process so that you can actually machine the new material and also new components. So as I mentioned, a single process cannot be solution. So I'm sure all of you know about different processes. Even if you are undergraduate, you have gone through manufacturing processes course, right? So you know, okay, micro turning, micro milling, micro grinding. Remember, those processes are all available at conventional or macro scale. Although our general sense tells that micro scale means the application of those at micro scale, but it may not be necessarily true, right? Because some of the things, behavior that you see only at micro scale. Like as I mentioned, there are some size limitation when you are machining near the grain size, or particle sizes. Then there are some size effect. There are some other properties that you can see at the micro scale only. So although we cover mostly micro and nano in that range, but some of those concepts can be applicable for traditional scales also. Okay, so conventional micromachining processes has these limitations, right? Because most of the conventional micromachining processes are contact based. That means you have a cutting tool, right? That is, contacting the workpiece, and then machining is a shearing process, right? So a simple example of machining, if you take like every morning when you put butter or spread, in your bread, you remember if you are using a knife to take a thin slice of butter, so it's kind of shearing, you are shearing through that, right? So machining, most of those like conventional machining, the cutting tool contacts the workpiece, there is some cutting forces associated with that, right? There is cutting forces in X, Y, and Z directions, right? So that means because of those, it's difficult to machine, very difficult to cut materials, especially if you consider tungsten carbide. You use tungsten carbide to machine other materials. So how you are going to machine tungsten carbide, right? Definitely there are some research on traditional machining, like using vibration assisted turning or electrical vibration turning, ultrasonic turning, that you can try to machine tungsten carbide, but in a common sense it's kind of difficult. So and machining at micro scale is even more difficult. Then there are some non-conventional machining processes that can actually get rid of that problem. That means if it is tungsten carbide or if it is aluminum or brass. Honestly, would you just look at electrical electrothermal properties, right? And hardness doesn't matter. Okay, definitely there are other properties. So I have one paper that we try to machine titanium and brass. Now, definitely, the like hardness or strength, those are not a like significant factor here. But some other electrical properties, electrothermal properties can play a role. So, non-traditional machining processes like EDM, ECM, laser, so those processes can really machine some of the difficult to cut materials, if that meets the requirement. Like for example, there is a minimum resistivity requirement for EDM. So if the resistivity is less than that, then definitely EDM will be able to machine those. But it also has some other challenges. Like for example, one of the more important challenges. So it's lower machining speed, heat affected zone, higher to surface finish. So EDM, laser, they use thermal energy, to remove material. So that means if you are machining the first layer, there is some oxide formation, right? And then you have some recast layer, right? After recast layer, you have some heat affected zone, and then you have material. So in the recast layer, definitely the properties are far more different than the base material, and the heat affected zone also, microstructure, phase transformation happens, so things change, right? So how actually you can get rid of those, okay? You can come up with a either sequential one by one or maybe concurrent. That means it is an individual process like electrochemical discharge machining, right? It's not like ECM and EDM separate. There are sequential process where you do EDM then ECM. But ECDM process, it kind of combines the electrodischarge and electrochemical dissolution, both mechanisms together, right? So you need to come up with some of those processes so that it kind of overcome the challenges from both sides. Okay, so you have challenges in the traditional side, then you have challenges in the non-traditional side. So while you are selecting or developing or innovating a compound or hybrid machining processes, you should be able to take care of those challenges. Okay, so that's why a single process may not be a solution nowadays. So and for additive and subtractive, the same thing. Additive and subtractive, they fight each other for some time, right? I remember I'm from the subtractive side. So when people started talking about additive at the beginning, it was difficult to kind of accept, because we said, no, it will not have the strength of the other processes, or when you make something very additive, it may not have that strength that when you machine some part. But now with the improvement of additive, now we came to a position where additive, they have taken care of many of those challenges, but still there are some challenges there. So now they say, okay, let's try to compound this. Okay, so now hybrid, if you say hybrid manufacturing, so it's mostly additive and subtractive. And we also call convergent manufacturing, where that's another term that you will hear in the next 5-10 years, convergent manufacturing. So that means two manufacturing processes are converging. Okay, so It's kind of hybrid processes, but then just a new term, convergent manufacturing process. Okay? Okay, so let's move on. So, compound and hybrid machining processes, it's a combination of processes or machines to produce parts that is more effective and productive way. Okay? So, I think I already mentioned the compound and hybrid machining, sometimes they are used as the same processes, but honestly they are not same. Okay? So when we say compound machining processes, it also has different terms. Okay? It has sequential machining and also asynchronous machining processes. So that means now one thing you need to fulfill the requirement. So, for example, you cannot take the part out of the machine. Okay, so if you do milling and then you take the part out and you are doing it in another machine, there is no more in the compound machining process. So wherever it is, whether it is compound machining processes or hybrid machining processes, it has to be on the same setup. Okay, it has to be on the same setup, and you are not taking out or reclamping your parts. So that's the requirement you need to fulfill, whether it's a compound process or hybrid processes. But compound processes, the thing is, you are using two or more processes one after another, and each process maintain their own characteristics. So that means if it is turning, it will follow the turning characteristics. If it is EDM, it will follow the EDM characteristics. Okay? So in the compound machining processes, two or more processes sequentially, can be applied in the same setup and without any need for recapping or taking out the part. Okay? So that's the compound machining process. In the hybrid machining processes, on the other hand, where the machine process itself has a different characteristics than two individual processes. So for example, if you're using EDM, then followed by ECM. So that's compound machining process. You can use the same setup, you can use same dynamic, like for example, DRS, water, okay, and you can control usually EDM, you use comparatively higher range of voltage, ECM, you use comparatively lower voltage. So you can do EDM and ECM in the same setup, keeping the same dielectric, or maybe changing the dielectric, one time DRS water and the time with the electrolyte. So it is possible. So that is compound machining. But hybrid machining is you are using the two concepts, electrical discharge, one concept, and you are using electrochemical dissolution. That means material is removing because of chemical reactions. So when you combine both mechanisms, in a single process, and that process has its own characteristics, so it becomes a totally new process. That is your hybrid process. Okay. Even assisted machining processes, is also hybrid process because, like for example, if you are machining and then you apply either like for example heat or cryogenic cooling, it can happen both ways, and so you are changing the material properties, right, at the interface. You are changing the material properties, and maybe because of the heat, there are some change in the microstructure and phase transformation. So you are adding two physical principles. Okay, one is machining, which is shearing, and another one either heat, application of heat or cryogenic coolant. You are taking out heat, but you are using two different energy sources in the same process. So that process becomes individual process with different characteristics. That's your hybrid machining process. Okay, so there is definitely clear difference between compound and hybrid machining process. So CIRP, which is kind of the I would say most prestigious organization for manufacturing, right? So SME definitely is another Society of Manufacturing Engineers is another prestigious organization, but CIRP is actually special. So they come up with definition of hybrid machining processes, It says a process based on simultaneous and controlled interactions of process mechanisms and or energy sources or tools having a significant improvement of the process performance. So as I mentioned, two physical energy sources or two physical principles that will be working together to improve the process. Okay, so that is your hybrid machining process. And most simply you can say 1 plus 1 equals to 3. So that means if 1 plus 1 equals to 2, then you are not getting any improvement, right? You are kind of so as I mentioned, sequential process. Sometimes you do one after another, and you get two separate outside. That may not fulfill 1 plus 1 equals to 3. But when you're talking about hybrid, real hybrid processes where two or more physical principles are working together, it should come up with a process that is 1 plus 1 equals to 3. So that means that individual process should be better than two separate processes. Okay, so that's the kind of concept. So again, so advantage again, that is also no specific advantage. Definitely advantage can vary over a wide range. So first advantage is you are actually starting a hybrid process to get rid of some of the challenges. So that would be your specific advantage, right? So what challenge? If it is low material overbreak like EDM, or if it is like poor surface finish like laser or EDM, so that is disadvantage and you are trying to get rid of that. So definitely improve productivity, improve surface finish performance, and also introducing new capabilities. So for example, you cannot really machine at the internal hole in a critical place. Now you come up with a process that allows you to do that. So that's kind of adding a new capability, right? Or hitting the boundary of miniaturization. So that's a kind of new capability that it can solve. Then eliminating preventing problems. I think that's the first thing I talked about, right? So whatever problem you are facing, you are trying to kind of get rid of that problem. So, like for example, ECDM that was doing, it not only reduces the surface damage by EDM, but also it provides more accurate shape than some of the ECM process. So you see, it get rid of the problem from EDM, it get rid of the problem from ECM, and it should perform better than EDM and ECM processes individually. So that's kind of the hybrid process. So characteristics, I think I already mentioned that, so this is probably I can skip this. To machine materials that was difficult to machine by any of the individual processes, but now it can be machined. Then reducing cutting forces, tool wear, improving productivity, surface finish, all capabilities. So those are some of the characteristics we talked about. Characteristics of the processes. Okay. So as I mentioned, if it is compound processes, then we have sequential, or it can be simultaneous, where it is hybrid process, but it has to be controlled iteration. That means if you cannot control, like for example, if you look at the history of the EDM, so at the beginning the EDM process was not controlled. We started during the Second World War, when there are some heavy machineries and some of those metals are difficult to cut. So then they found that this is part can really cut those difficult to cut materials. But it became controlled much later. So all the processes you need to control. So chemical dissolution, you can put something in a solution and it will be after 7 days, material will be lost. But you cannot really control what shape do you want if you do that, right? So the machining process you can only claim when you will be able to control that. And you will be able to control the material you will break, you will be able to control what shape do you want. So it should be a control. Then iterations, we talked about iterations. Sorry. Okay, then definitely the effect on the process performance, the better real rate. I think the two you already talked about those. But the final thing is overall improved performance. One plus one equals to 3, right? So it should perform better than two individual processes. Now, I think I mentioned one thing. Whether we were talking about hybrid or we were talking about compound, the important thing is it has to be on the same setup, right? It cannot be two different machines. So the most important thing is the development of that machine. Okay? So which is capable of creating two processes in the same setup, or maybe two or more physical principles applied on the same setup. So the first thing is we need to develop that machine tool which is capable of I say like both conventional and non-conventional machining, but it doesn't necessarily. Sometimes if you combine two conventional processes, it can be also hybrid process. Or you combine two non-conventional processes, it can be also hybrid process. Right? Then motion and process control. Just now what I said, you cannot just have the physical principle to work and get it initiate. It has to be controlled. Okay? It has to be controlled shape. Controlled axis, you need to consider the axis resolution, you need to consider the minimum feature size, how you can control those and obtain that. Then the process development to achieve the necessary accuracy and so most of the manufacturing processes, the research area, we kind of work on the process development, right? How you can come up with the process that can help you to achieve something. Then another thing is in situ measurement and inspection. Okay, some of the for hybrid machining processes. Sometimes I think if you do research, you will see that sometimes we take out the part to take the CM or some of the analysis, but we don't be able to use that, right? So usually what we do when we do the research, we try to destroy a few samples to do the characterizations. But when you are looking at real life applications, you cannot really characterize those and then apply. So you need to have in situ measurements or on machine measurements. Okay, so that you machine that there and then you kind of use or in situ measurement like on machine camera or laser or whatever you need. Okay, and you should be able to measure there. And before you can take out the part for final use. So those are kind of the four processes. So you have four regular technologies. So machine tool, this is a must. You need to have a machine tool, and then for that machine tool you need to have position and motion control, or machine measurement, and then process development. To make things accurate. So I think we talked about that, so skip that. Now, few things you need to consider. For example, for when you are talking about machine development, the rigidity, vibration, of those machine. Then you are doing some vibration analysis for the machine, which is very important. So your target is to make the machine lighter, but at the same time, lighter will also introduce some vibrations, right? So the machine rigidity is also important. Then the thermal expansions should be minimized. Then some like for example, advanced sensors and instruments can be employed. Another important thing is that the hybrid machining, the clamping and re-clamping error needs to be removed. Because, like for example, I can give you one example. So, for example, you have in your machine you have some spindle runner. Okay. So, before, like for example, before starting any machine, what you do? So you try to measure the spindle runner. Then you think how I can get rid of the spindle runner. Like for example, if you are doing turning, like for example, if you are doing turning and there is some run out and you define 0, 0, then if you do just one pass, to define 0, 0, then after that it becomes coaxial. If you don't take it out, you do all the machining there, there is no spindle run out there, or you are doing milling, if that spindle run out and you get rid of that spindle run out, until you take this out, there is no run out there. Okay, so that's one of the goal of the hybrid machining process. So you prepare your workpiece and tool one time, then you kind of complete all the processes that you need, and then that time you can also take this part. So you kind of avoid reclamping. Okay, so by avoiding the reclamping, you can actually bring down the accuracy of the sub micrometer. So that is less than micrometer. Using a traditional machine. So maybe you have a cheaper machine that has 20 micron spindle run out. Then the first thing you can do is after installing, you can try to do some maybe reducing the tool diameter or doing some initial turning. You can actually get rid of the spindle run out, and then you can actually really obtain some micro level accuracy. Okay, so using a simple, inexpensive equipment, you will be able to actually obtain very highly accurate, machine. Okay, if you actually follow that. So this is one of the equipment. Actually, my PhD supervisor, Professor Raman. So he has his startup company. So what we did our PhD, we kind of worked on the development of those. Okay, that time. I think now the equipment is available. So for this, the most interesting thing was, like for example, here, this is an interchangeable. Okay, so let me probably. So here, so this is actually an interchangeable. So you can use the screw. There are some screws here, so you can actually put this back and then take it out. So you can use separate attachment for, like for example, die-sinker, wire EDM, then wire EDG. Then I think recently he started laser also. So those are, like for example, the same setup. When you take this mini spindle out, you can put this wire EDM, then it will work with the wire EDM machine, or you can use the die-sinker EDM, or you can use turning. Then there is some in situ measurement also. So the thing is, you need to think creatively how you can actually use the same machine, but you can have interchangeable parts that you can actually take out and put your interchangeable part, and then you can do a new process. Like for example, now if you are working on like for example, you are a new PhD student, think of a new process. Just think what equipment your previous student are using, and how you can actually probably modify that by developing an interchangeable part or device, and you can put it back into the equipment and whenever you need it. So that's kind of a concept actually for this multi-purpose machine tool. Okay, so yeah, so definitely I have some contribution in the development of this also, but I think right now this is commercially available. Okay, so sorry about the interruption. Okay, so classification. I think I talked about this. Then for classification, I believe I talked about that classification. So the first group is compound micromachining processes, or sometimes we call sequential processes. And then second group is hybrid processes, and I think I made the differentiation before, right? So in the hybrid processes, sometimes we call mixed processes, sometimes we call assisted processes. So what's the difference? So in the assisted processes, you have a single process which is dominating, we call primary process. Like for example, vibration assisted EDM. So in EDM process is dominating, right? The primary process. And vibration is a mechanical, assistance, right? So you are adding the mechanical assistance, in the EDM process. And that mechanical assistance may not be responsible directly to remove the material, but it can aid in improving the material work. So that is your assisted process. Again, we're going to go much detail for each of those, okay, later. Today is just introduction. So that's your assisted process, right? You have a primary process that is responsible for the material work, or machining, and then another process is a secondary process which assists in probably one of the parameters or maybe all of the parameters, right? So vibration assisted EDM, it helps you, to remove the debris, from the machining zone, reduce the ineffective pulses, which actually helps in improving the surface finish also. So it helps in overall, improvement of material weight and also surface finish. But sometimes the dimensional accuracy may suffer, okay, because of that additional action of the vibration. But mixed processes or concurrent processes, like for example, I talked about electrodischarge machine. Let's speak another process. Like for example, abrasive assisted grinding or something. So you know that in the grinding process, you have some mechanical particles, right, in the grinding wheel, and then you use some coolant, right, and to do the machining process, right, or slide, to do the machining process. Now just think, what about if that slide itself has some chemical, properties, like for example ECM, you use some electrolyte, right, to do the chemical reaction and remove the materials. Whatever I use some electrolyte, in the abrasive slide for the grinding process. Now what happened? In the grinding process, sometimes there is some oxide layer forms, right? And that kind of sees the process or reduce the, material weight. Now if you have those chemicals, with the abrasive, that helps to do some chemical dissolution, right? Now the overall performance is improved. Now you cannot really separate two things. You can definitely do more investigation, but you cannot really separate that, okay, this time of the machining only chemical reaction happens, this time only mechanical reaction happens. It is an interaction, right? So that's your hybrid process. So you have both electrochemical dissolution and mechanical, abrasion. Both are actually playing, role at the same time. So that's your hybrid process or mixed process. So this is the difference between assisted and hybrid process. So understanding, I think I gave three examples, and I will cover lots of examples. As my time allows, I'll try to cover a lot of examples in the next, while we cover individual processes in detail. But just in order to understand hybrid processes, the next few slides, we already gave some examples, but next few slides are very important. So you need to understand, how machining happens, right? The traditional machining, we talked about, mechanical contact, right? You have tool which is harder than the workpiece material. Then, there is some shearing happening, just like the butter we talked about. If you have a material that should be able to scratch on the other surface, that means there is the harder material than other, right? And that should be able to machine that material, able to shear through. Then we have some abrasive, can also remove the material. So those are traditional, they are non-traditional, and those are mechanical. So you have mechanical contact, you have abrasion. Then non-traditional use different types of energy sources. Like for example, electrical discharges, EDM, they use electrical discharges or pulses. ECM, they use electrical dissolution. Then melting and evaporation, like laser, it applies, then it raises the temperature, melting, evaporating, right? So different processes, use different kinds of energy sources to remove the material. So the goal of the hybrid processes is to combine some of those energy sources. If you combine two energy sources, it should be a new hybrid process where material is removing simultaneously from the two sources. So that's the kind of like way to invent hybrid machining processes. So, and I think I talked about assisted and combined, so I can skip that. So this is kind of an example of how different sources can actually happen. So I talked about mechanical assistance, I talked about electrochemical assistance, or thermal assistance. Sometimes you can either apply heat or you can take out heat, cryogenic machining based on what is your goal, right? We talked about that, but all those processes or all those assistants actually can improve the performance, right? So I need to go a little bit faster, right? Yeah. So I'm almost there. So okay, but I didn't know what to go too fast or skip. If you have any question, I'll be happy to go over any of the slides. So this is just an example. How actually different processes happen. I'm just taking one example. So this is for applied vibration assistant in microEDM. So the traditional microEDM, so here you see the machining time for the traditional microEDM without vibration is here. Now, when you apply the vibration assistance, it doesn't matter which parameter you are applying. You see, for all cases, it's kind of there is a significant reduction in the machining time, and we talked about that, and we'll cover vibration assistant more in detail. But usually the reasons are when you are actually going deeper. That's why the workpiece leg is that is. If you are making holes, very thin part where you do not see the effect that much. But when you are machining highest ratio holes, like for example more than 20, maybe 50, or around that, you see that after some time machining becomes unstable. It's not going anywhere, right? Then you need some further assistance to flush away, get away from the machining zone. So if you are using vibration assistance, definitely it creates some pressure. I think if you search vibration assistance, I have several papers, and one of them is modeling paper. So it creates some sinusoidal formation of the pressure. So you have, when the gap is closing, you have the increase in pressure, then you have decrease in pressure, right? That also helps to get the debris out, and then it improves the spark efficiency, and so there are several phenomena that's happening, and then definitely machining time reduces that, the material removal rate is increasing, the surface finishing improves, and also I think we found that vibrational accuracy will a little bit off form, but the edges or surface finish is very good. The same actually for ECM. The next one is ECM. So you can see that actually there is actually significant reduction in machining time, especially when you are actually going for higher application. So for both microEDM and micro-ECM, it improves. Then this is just another example. If you are doing electrochemical micromachining, electro-discharge micromachining, then if we use this is sequential actually one after another, but it's still it actually helps in reducing the machining time for the finished part, and also it actually, if you are using sequential processes, it can give you higher cavity depth with lower edge radius. Okay? Sometimes edge radius actually is difficult to control in the ECM process, so things become actually larger. But EDM actually you can control that, but if you use two processes simultaneously, it definitely is better. Now, how the performance is improved? So it is not, otherwise it is not just 1 plus 1 plus 2. So if you have A, B, two processes, so the performance should be the performance for A, performance for B, plus performance for A times B. So that means there should be some additional performance improvement for the concurrent applications also. Now, so this is kind of, I think I can just go quickly away. I'll share those slides with all of you. Okay. So this is just the advanced manufacturing processes based on different energy sources. Okay. So can I take? How long can I take? How long can I take? 5 to 10 minutes. Over? Yes. Yeah, maybe 5 minutes. I will take. Okay. So this is important. So if you know that which process use which energy source, later you should be able to combine those. So here, ultrasonic machining that use ultrasonic vibration, then one of the machining will use hydraulic pressure, that is one of the machining. Then you have ECM, electrochemical, then you have the thermal, you have EDM, electron beam machining, laser beam machining, ion beam machining, plasma jet machining. So it has the energy sources, and then you have the tool used for machining, and then the media, transfer media that actually helps to transfer the energy from tool to the workpiece. So now once you know those, now if you plot the same processes and energy sources in both x-axis and y-axis, just like this. Okay, so if you just plot those here, mechanical, abrasive, ultrasonic, electrical, chemical, laser, magnetisms, then same here, abrasive, ultrasonic, electrical. So you are doing the same on the left side, like in the column and in the row. Then you just go row and column and see whether you can combine two processes and come up with some new hybrid processes. So you already see there are some. Like for example, ECM and ultrasonic. So you can use ultrasonic assisted EDM, right? You can use some ultrasonic vibration with the ECM. Or laser and EDM, laser assisted EDM. Okay? So similarly, you see some question marks. So that means there are some processes that people have not explored. Okay? So this is I am exploring right now, ultrasonic vibration assisted laser, but you can also try to come up with some new processes. Or sometimes you can see researchers have used sequential process. Think about how you can actually make that hybrid process, not sequential process, right? So how you can actually add those two in one setup to do hybrid processes. Okay, so this will be so that I will share the slide with you and you can share it with everyone so that we'll go more in detail for each of those. Okay, but I think this is kind of the introduction for today. So after that, so this is I think the same just with example. Maybe in one of the lecture we'll do some case study, some discussion. To see how we can come up with some idea to solve some problems, okay, for this in the process. Okay, but I think the last few slides is really a guide to think about innovating new hybrid processes. Okay. So thank you everyone, and thank you very much.
Thank you, Mr. Pavel. So participants, do you have any questions?
My research area, so I cannot really coming out of that area. So my recent research has been how I can actually use some of those hybrid processes, for improving the performance of the LED. Okay, like people are using those. So if you look at LED, people are using ultrasonic assisted LED process. Okay, or sometimes now they are trying to do, they are saying, sequential, they are doing some sequential process. They have the laser beam and the milling tool at the same machines, commercial machine. All they are taking the concepts from what have been done before, right? And just trying to apply those in the new area. So if you really, I think some of those concepts, if you apply for any, that will provide a new concept. And I think just feel free to start a new initiative.
Sir, you know, multi-purpose machine you have developed. So, in that, can you think about the direct-like arrangement so that you can, instead of changing the setup, individual setup like for trading, for milling, for writing, you just have it like a direct and you just integrate the thing automatically in the setup.
So you are saying like different in the same setup, different setup? Yeah.
Have you performed like that?
No, but as I mentioned, it can be done. But I remember for my case, sometimes we are lazy to interchange those, right? So I also did some modification myself. Like for example, power CDM. When we do power CDM, I try to use a separate, fluid circulation system. Just develop a separate fluid circulation system, or maybe a separate tank. That when I am done with that. So
in that case, you have to change the workpiece alignment also.
no, so
Again, in the wide area, just to have some that micro area.
So the goal is you should not change, you should not reclamp. If you clamp it again, then you are losing, there is a position error is taking place. So you need to avoid. You can use different processes if you tool and what it should be there. You can bring that to different stations, I would say. Different stations and do different processes. But in tools and what we should be there. Yeah, very good question. So, that's the thing we're talking about. So when you are doing micro machine, right? Again, there are several steps. You have macro, then meso, you have micro, right? In the micro machining, when you are machining, maybe where hundreds of grades and boundaries are involved in there, right? So definitely the microstructure is changing there, and some phase transformation can happen. Phase transformation can happen because of the mechanical, the pressure, the contact, or it can happen because of the heat generated during the machine, right? If you go down the phase transformation temperature, especially for titanium, on your machine, you found there is some transfer of because the temperature goes high. So microstructure can change at the micro machine level, right? It really depends on also how many grades in that space that you are machining.
So is the change of property desired?
Change of property is again, that's also another business area food. Change of property cannot really avoid. So better is think how can we introduce some positive change in the area. Like for example machining. Previously people did lots of machining and then heat treatment because of the machining. Now they think, okay, why cannot we just do maybe machining and then some finishing with home milling to introduce some compressive residual stress, which is actually beneficial. Okay? So you don't need to do heat treatment or something like that. So, and for EM also, previously I remember our target was how to reduce the recast layer, how to get rid of those, do some grinding or some other compound process. Now I'm doing research, okay, how we can actually make that modified surface, useful. Like maybe for biocompatible, improving biocompatibility or torsion resistance or wear resistance, what would be the beneficial thing? So sometimes you turn that, what is disadvantageous, you turn that into an advantageous thing, just by controlling it. So
same is true with the nano machine. Nanoscale machining, same is true. Like characteristic of the material will change.
For nanoscale machining, that's a very good question. So for nanoscale machining, it can, it can change. So I remember I did some nanoscale EDM, nano EDM, okay, and we did, when you're doing nano EDM, you are machining a single brain, inside a single brain, right? So the properties of that single brain will change. Okay, so yeah, so the properties of that single brain will change. So yeah, so you can as a machine create the right, even some of those processes use, the gas assembly also. Okay, like for example, EDM, you high speed oxygen, gas, or even air to move the battery. So yeah, so you can definitely come up with some of those things. Like for example, one of the benefits of using, like for example, cryogenic machine. You are using the cryogenic nitrogen, and as soon as you spray it comes into the atmosphere and just goes into the air, right? So although you are beginning as a liquid and you are supplying as a liquid, as soon as it comes to the normal temperature, it just goes into the air and it's not polluting the air or anything. So that's why the cryogenic machine they are talking that it's a sustainable machining processes. Although it may not be
so it was a very nice career and I think all of you enjoyed it.